Good afternoon, everybody. So, it's an honor and a privilege to welcome you all to a very special occasion, that is, the fifth Bibha Chaudhuri Memorial Lecture in conjunction with the 102nd PRL Ka Amrit Vyakhyan. Today, we gather here to celebrate the spirit of scientific inquiry and to pay tribute to two remarkable legacies. First is that of Dr. Bibha Chaudhuri, a pioneering physicist whose contributions to cosmic ray research remain an inspiration, and the rich tradition of intellectual discourse upheld by the Physical Research Laboratory through the Amrit Vyakhyan series. Today, we have a talk by an esteemed speaker, Padma Shri awardee, Professor Sharda Srinivasan from National Institute of Advanced Studies, Bangalore. She'll be delivering a talk on a journey in archaeometallurgy. To begin this distinguished event, I have the honor of inviting Professor Anil Bharadwaj, Director PRL, to address the gathering. Sir, we request you to kindly grace the audience with your words. Thank you.
Suswagatam, Namaskar, Suaprahan, Abhivadan, warm greetings and hearty welcome to the fifth Dr. Bibha Chaudhuri Memorial Lecture and the 102nd PRL Kamrit Vyakhyan, as well as 26th PRL Kamrit Vyakhyan 2.0. PRL has instituted Dr. Bibha Chaudhuri Memorial Lecture in the year 2020 to honor and commemorate the life and work of Dr. Bibha Chaudhuri, whose major scientific career has been spent in PRL, starting from the year 1959 and then formally joining PRL in 1966. And it was none other than Dr. Vikram Sarabhai, the founder of PRL, who actually recruited Dr. Bibha Chaudhuri as a faculty in PRL. Dr. Shivavati Goswami will be describing more details about the work and legacy of Dr. Bibha Chaudhuri. But I would like to tell you that her work in the area of elementary particle physics and cosmology is one among the few well-renowned work which she has carried out while working in PRL. The Bibha Chaudhuri Memorial Lecture we started actually in the year 2021, and this is an annual memorial lecture where we select very distinguished women scientists working in the field of science, technology, or social science. So the scope is very wide, and we like to invite eminent speakers. Today, we are fortunate to have Padma Shri Professor Sharda Srinivasan with us, who is the speaker for the fifth Bibha Chaudhuri Memorial Lecture. And she is an archaeometallurgist. And archaeology, if you talk about in PRL, is a field which has been pioneered by Professor D.P. Agarwal, who has been the faculty at PRL and well-known figure in India and internationally. And he passed away a few days back. So we will have Professor R.D. Deshpande describing some of the very important contributions of Professor D.P. Agarwal in the area of archaeology. And I would request all of you to pay homage to Professor D.P. Agarwal with a 1 minute of silence, please. Thank you. So once again, let me formally welcome all of you for the 5th Bibha Chaudhuri Memorial Lecture and the 102nd PRL Kamrit Vyakhyan. And I also thank all the colleagues who have joined us live on the PRL's YouTube channel for this event. I now request Professor Shubhabati Goswami to tell us more about Dr. Bibha Chaudhuri and her work. Over to you.
So as Professor Bharadwaj said, that Bibha Chowdhury spent a substantial amount of time in PRL. And Dr. Bibha Chowdhury actually was the first women high energy physicist in India. And, you know, when at a time when there are very few women even doing physics, she pursued a research career in experimental physics, which is a pioneering achievement, as well as a very inspirational phenomenon. During 1938 to 42, when after her MSc from Science College in Calcutta, she started working with Professor D.M. Bose in Bose Institute in Calcutta, and they did some path-breaking work in identifying a cosmic particle which is heavier than electron. And what they did was they used the photographic emulsion technique, exposed these photographic plates. They went to the northern part of West Bengal in Darjeeling, and they found some evidence of a particle which is more massive than the electron, about 150, 200 times. And later it was thought that, this could have been a Nobel Prize winning discovery, because Powell, in 1950, Powell got the Nobel Prize for discovery of pi meson. And whether there is a lot of discussion on whether it was a chance of missing a Nobel Prize. However, and they published 4 Nature papers. If you read the papers, then in their paper, they never mentioned about the pi meson. They call it mesotron, and they had different masses, which was not exactly the mass of the pi meson. They reported several observations with a particle having different masses. So the main problem which was realized later was they were using photographic plates, which are called half-tone plates, which means the emulsion was on one side. And what Powell used was full-tone plates, where the emulsion was on both sides, so it has a better sensitivity and resolution. Actually, they had understood that, it would be good to have these full-tone plates and repeat the research. However, there was a financial issue in procuring these plates, because those were not made in India. They had to be got from outside, and so this experiment could not be continued. But Bibha Chowdhury realized that, cosmic ray research is very important. And she joined Cosmic Ray Research Laboratory of PMS Blackett in 1940, in 1945 in University of Manchester. And she did her PhD in extensive air shower arrays. Before her PhD, she already had 4 Nature papers. And then she went to pursue PhD with Blackett, and she worked on cosmic ray air showers. And after she submitted her thesis, she came to TIFR. She spent about 4 years in TIFR, and then she went abroad. She went to various places like École Polytechnique in Paris. Then she was in Michigan, and then MIT. And she worked on study of cosmic ray air showers actually extensively. And it is not very surprising that, Sarabhai was interested in her, because the interest in PRL was a lot of interest on cosmic ray research, especially of Sarabhai. And she joined PRL in 1950, first as a CSIR SRF, and then in 1961 as a pool officer, and finally in 1966 as a fellow. She spent 10 years here. She mainly worked in the Kolar gold field in collaboration with scientists from TIFR on high energy muons, on detection of high energy muons coming from extensive air showers in cosmic rays. After 1976, she went back to Calcutta. She worked with scientists at Shah Institute, VECC, University of Calcutta, IACS. However, what was very surprising for the later generation was that although in spite of her pioneering contribution, Bibha Chowdhury was very invisible. Like the next generation has hardly knew about her. Like that applies to me also. Her trajectory is like from Calcutta University to PRL and then Shah Institute. She worked with colleagues of Shah Institute, Calcutta University. These are the places where I have also been, but I didn't know about her. And there was a book written by science historians Rajinder Singh and Suprakash Roy on Jewel Anand Bibha Chowdhury, which brought her again into the limelight. And in 2099, IAU named a white yellow dwarf star as Bibha in honor of Dr. Bibha Chowdhury. Since Bibha Chowdhury has spent majority of her work life in PRL, it's natural that PRL organizes a lecture in her memory, although she was largely forgotten during her research time. But now we are acknowledging her contribution, the pioneering contribution she made, especially as a women scientist, which is an inspiration for several women, and especially the women who are doing this research. So with this idea, we started in 2021, and we are having the 5th lecture now. And so this is our, this is how we are paying homage to the pioneering scientist. So with this, I would now like to call Professor Deshpande, because as Professor Bharadwaj mentioned, that Professor D.P. Agarwal, who was in PRL and worked on the topic of today's subject, has recently passed away. So we thought that it's a good opportunity to also remember him. And Professor Deshpande has worked with him, so he is the best person to enlighten us about his work. Deshpande.
Okay. Good afternoon, everyone. And thank you very much, Professor Shubhavati, for this opportunity of saying a few words in honor of Professor D.P. Agarwal, a doyen in the field of archaeology, a former senior professor in PRL, and chairman of the areas archaeology, hydrology, and continental paleoclimate, and OCECS, Oceanography and Climate Studies. So that was the time. And what could be more befitting tribute to such a great archaeologist on this occasion, when another great archaeologist is going to speak about the archaeology and particularly the archaeometallurgy. So I think this is the most befitting tribute to him. And on my part, this is quite nostalgic because I was lucky to have spent 4 years with him from 1989 to 1993. And during that period, Professor Agarwal used to travel extensively in Himalayas from Kashmir, Ladakh, Kumaon, Gadwal. And I, being a geologist, my role was to initially look for the depositional environments of the lakes. So that's how it is. And let me tell you something about Professor D.P. Agarwal. Professor D.P. Agarwal was a renowned archaeologist and historian of India, whose contributions to the study of ancient civilizations and cultural heritage have left an indelible mark on global understanding of India's ancient past. As I mentioned, he was senior professor and chairman of 3 areas here. There used to be an archaeology hydrology area in those days. He was born in March 1933 in Almora, and he passed away 2 days ago on 24th of March 2025 in Kashipur. And his last rites were performed at Mukteshwar and Hapur. It may be very important to let you know that how PRL played important role even in the archaeology, though we do not have very active archaeology research as of now, but in those days, it may be very useful to recount. So Professor Agarwal had linkages like many other people have with Allahabad University, BHU, TIFR, and then PRL. Many stalwarts have this kind of relationship. So he did his BSc from Allahabad University in 1954. Then he did his MA in archaeology from Allahabad University. BSc was in chemistry and then MA in archaeology. Then he actually joined ASI as an exploration assistant in 1958. So 1958 to 60, he worked as an exploration assistant in GSI. Then 60 to 62, he did postgraduate diploma from the School of Archaeology in ASI. And in November 62, he joined TIFR. And you may know that Professor Devendra Lal also was from BHU and then he joined TIFR. At that time, many stalwarts were there from BHU to TIFR. So he joined TIFR and worked there from 1962 to 1973. And around 70s, the geophysical research group of TIFR in entirety came to PRL. So at that time, Professor Devendra Lal came along with him, Professor Krishnaswamy, Professor Somaya Julu, and along with them, Professor Agarwal also came here. So to be precise, in February 73, he came to PRL and he worked here in successive capacities as fellow and associate professor, senior professor, and chairman. So he retired in 1993. There are important things that something which, apart from ASI, the things have been done by PRL that I would like to mention. And with reference to Professor Agrawal, that he worked in multitude of domains like archaeology, history of human settlements, environmental studies, with a focus on understanding India's prehistoric and protohistoric periods. And he contributed substantially to advancing the research on Indus Valley civilization, ancient metallurgy. We are going to listen from Professor Shada today on that, and impact of climate change on historical societies. Now, to be able to do these kind of things, one has to have interdisciplinary approach. And the interdisciplinary approach 45 years before now was not so common a word than what it is now. So even in those days, Professor Agarwal nucleated the application of radiocarbon and TL to archaeology, then mineral magnetism, then paleoenvironmental studies, because he wanted to understand the depositional environments, then limnology, palynology, micropaleontology, isotope application, and retrieval of traditional knowledge. So all these things were from 1975 to 1993 were performed in this institute, and such a diverse group, including the palynology group, was there. And if I just recount the important contributions, so in paleoenvironmental studies, he tried to establish the relationship between ancient human societies and their environment. And that's how we did the deposition environment studies in the high altitude lakes in Himalayas. Then radiocarbon and thermoluminescence dating. So the radiocarbon lab in TIFR was established in 61. 1959, it started in 61. When he came, he established the lab here in PRL. So I must recount at this moment Dr. Sheila Kusumgar and Professor Singhvi, who contributed. Then archaeometallurgy, about which we are going to listen today. So we explored the history of metallurgy in India, shedding light on the technologies, advancement in ancient civilization, then prehistoric archaeology, traditional knowledge systems. And he was a prolific writer. He has written 14 books. So he has written 14 books and 250 research papers. So that is what was his dimension of activities. And his legacy extends beyond his academic achievements. I would like to say that he fostered a deeper appreciation of India's scientific and technological heritage, particularly challenging the Eurocentric perspectives which were there in 60s and 70s. And his passion for knowledge and dedication to research will continue to inspire generations of scholars. He will be deeply missed by his colleagues, students, and all those who benefited from his profound insights. And on behalf of all of us here present, we pray Almighty that may his soul rest in peace. Thank you very much. I will invite Professor Pallam Raju to kindly introduce the speaker today and for the program.
A very good afternoon. It is indeed a great pleasure and an honor and a privilege for me to introduce today's Vyakhyankarta, 102nd Viral Kamrat Vyakhyan, and 5th Bibha Chowdhury lecture speaker, Professor Sharada Srinivasan. Professor Srinivasan obtained her BTech from IIT Mumbai in 1987. It is very interesting to note that she and her colleagues co-directed and acted in and choreographed an English feature film called The Nuclear Winter, which actually won the Cannes Award in the special category in 1988. After completing her master's degree in the University College London, wherein she worked on the South Indian bronze sculptures, and that happened in 1996. Professor Srinivasan made pioneering contributions to the study of archaeology and history of art from the perspective of exploring engineering applications. She worked on artifacts in the Government Museum of Chennai, British Museum, Victoria, and Albert Museum, London, ASI, among others. She has several awards to her credit, and some of them include DST SERC Young Scientist Fellowship, Flinders Petrie Medal in 1989 from University of London, Materials Research Society Malti B Ethno-Archaeology Award in 2005, Materials Research Society of India Medal 2006, Indian Institute of Metals Certificate of Excellence in 2007, Dr. Kalpana Chawla Young Women Scientist Award in 2011, Distinguished IIT Alumnus Award in 2012, and Indian National Academy of Engineering Women Engineer Academia Award in 2021. Professor Sharada Srinivasan is an elected to an international honorary member of the American Academy of Arts and Sciences in 2021 in the field of archaeology. She is a fellow of Royal Asiatic Society of Great Britain and the World Academy of Arts and Science. She received the Padma Shri Award from the Government of India in archaeology in 2019. It is a rare combination that we have a technologist and cutting across the fields into archaeology and making pioneering contributions, making the country proud, and bringing to light the Indian forms of arts and the sculptures to light. With this brief introduction, I invite Dr. Sharada Srinivasan to please come onto the dais and deliver the 5th Bibha Chowdhury Memorial Lecture and the 102nd PRL Kamrit Vyakhyan on a journey in archaeometallurgy. Please put your hand together for Dr. Srinivas.
Okay, yeah, it's better. Yeah, sure. A very good day to you, and respected Director Dr. Anil Bharadwaj, Dr. Palam Raju, Dr. Deshpande, Dr. Subrapati Goswami. I'm really very privileged to be here in this very august setting of the Physical Research Laboratory, and very grateful to be here amongst you all. And it's really a momentous occasion for me to be delivering this lecture in memory of two stalwarts. One, Dr. Bibha Chowdhuri, as a cosmic ray physicist and high energy physicist who's also worked on the Kolar gold fields and so on. And that was also a starting point and inspiration for me to work in physics. And my first degree in IIT was in engineering physics. And it's a keenly felt aspect in terms of promoting women in STEM disciplines. For instance, when I started out in IIT, there was just 1 in 20 of us. So it is very heartening to be giving this lecture in honor of another very great woman scientist of this country. And of course, what can I say? I had no idea at the time of giving this talk, that at the time of accepting this, that it would be such a momentous occasion. As an Indian archaeometallurgist, there are no words really to describe it, because a physical research laboratory for all of us, in a way, those of us who worked in archaeological sciences, was almost synonymous with the name of Dr. D.P. Agrawal, who made so many outstanding contributions as mentioned here. And he was also a great mentoring figure. I first had the occasion to meet him in 1998 at the Materials Research Society conference in Boston, where I was also presenting in archaeometallurgy, and I had all my concerns about going back to India and working in this difficult discipline, but DP was very encouraging, DP as we all knew him. And he also came to NIAS in the early 2000s and spent time with us, and myself and Professor Ranganathan have a lot of very good memories of that time as well. Of course, his health was already failing and he was having great difficulty speaking, but he was doing a lot of good work also in Almora, and what can I say? It falls upon me to give this memorial talk in really one of the stalwarts of our disciplines. So I have to also say now that here in PRL and also seeing the photograph of Vikram Sarabhai, who has also been in a way a very motivating figure for me through my father, Dr. M.R. Srinivasan, who worked in atomic energy directly under Dr. Sarabhai in the nuclear power sector and went on to become the chairman of the Indian Atomic Energy Commission. And in fact, he has turned 95 this year. And that's why I thought I should also mention him as a seminal figure who also shaped my interest, because I was interested, of course, in taking up engineering physics, but he was indirectly also responsible maybe for the career turns I took towards archaeological sciences, because he would constantly talk about the uranium-thorium cycle, which was used to generate atomic energy, and the nuclear chain reaction and fission and fusion and so on. And in a way, the studies that I'll be talking about today involving the use of lead isotope analysis in archaeology is also an offshoot of that kind of line of thinking. And my mother, Geeta Srinivasan, who I should say, as a woman academic, she really kind of inspired some of my crazier activities and adventurous interests in archaeological sciences and so on. Well, this morning I already showed you the slide where I was also making the connections with the ways in which art, dance, sculpture, and cultural interests all came together in my particular case, as I was also pursuing Bharatanatyam. And some of my interest in studying the celebrated Nataraja icon, which Ananda Kumaraswamy, who was also a Renaissance personality, a geologist who turned into an art historian, and he famously described this icon as poetry, but nonetheless science, because he saw in it, in the Shaiva Siddhantic translations, some notions of the Panchakritya, or the 5 activities of God, as he put it, which is of balancing Srishti or creation with Samhara or destruction, with the perpetual cosmic cycles of creation and destruction. And this was an icon which also inspired a lot of philosophers and thinkers across the world, including Carl Sagan, who wrote that the imagery held out a premonition of modern astronomical ideas. And the quantum physicist Fritjof Capra was moved enough to compare Shiva's dance to the dance of subatomic particles. Of course, this is a pre-modern cultural icon, so there's no direct comparison in that sense with modern science, but it is more in the metaphoric context. And this image has also been donated by the government of India to the CERN Cosmic Lab, which you're seeing there. So my early interest was also to try and understand the metallurgy and the manufacturing processes and so on. And now that I'm here in Gujarat, of course, there is another very important dimension that shapes our understanding of our cultural settings and so on in India. And I first visited Dholavira, which is a Harappan site in the Kutch region. And there is also a very beautiful bronze which was uncovered in Dholavira of a figurine which we might describe as a dancing girl up there. And of course, you're all familiar with the celebrated Mohenjo-daro dancing girl. And what is quite interesting is also there are these various facets of continuing elements which we still see discernible in several aspects of our cultural heritage. For instance, when I was at Dholavira at the excavation, I could see that the Rabari women were wearing these bangles, which are just like what you see in the Mohenjo-daro dancing girl. And even in the Nilgiri region, you see the Kota women, they wear their hair to one side in the Kolkot, which is just like the Mohenjo-daro dancing girl. And this is all the way down in Tamil Nadu. And you see the hand on the hip is also very much a part of the Bharatanatyam dance tradition, drawing from Sadir. And the Dhokra bronze casting in Bastar and Eastern India, they use these very wiry elements of the wax to make up the model, which is also quite reminiscent of what you see in these very archaic bronzes. And of course, this is a Bronze Age civilization. So some of the early samples that we saw of the copper alloys, which I analyzed, were typically of low-tin bronze. And speaking of Professor D.P. Agrawal, he had done a lot of remarkable work also on the copper hoard cultures and also on the Daimabad bronzes, which was a very important hoard which was found in Maharashtra, which showed some archaic features going back to the Harappan repertoire as seen in this elephant from Daimabad, which of course, he did have some arguments about whether they were actually late Harappan or not. But anyway, this was all a very exciting time when these kinds of artifacts were coming to light and being analyzed. And it's interesting also in the context of the bronzes that I will be talking of predominantly today, the South Indian bronzes, that you can see that Daimabad bronzes, they have these holes under the elephant, which suggests that they were having bamboo poles put through them and being taken out in procession, perhaps, in the way that you still see the icons being taken out in procession in southern India, as seen with this famous image of Shiva as Rishabhavahana. So this is perhaps very ancient practices. And I'm also seen here at the workshop of Radha Krishna Stapati, who also won a major award last year for the beautiful Nataraja, which is in the Pragati Maidan. And bronzes in general were made by the process of lost wax casting, where they were first fashioned out of wax and then invested with numerous layers of clay. And then the mold is heated to melt out the wax, and then metal is poured in to get the shape of the casting. And this is what you typically see here in Swami Malai, where the mold has been fashioned. The model has first been made of wax and then covered with numerous layers of clay using the alluvial clay from the Kaveri. And then the mold is heated and the wax is expelled and metal is poured in. And this technique is also, of course, described in the Indian Shilpa Shastras, including the Manasara and Manasollasa. And there's also a lovely reference of the Tamil mystic poetess Andal, who in the Nachiyar Tirumori likens the downpour of rain from the clouds to the metaphor of the release of wax from the mold in the process of the metal casting. And she says, "Ulle ulle meligu urki vengalamutru." So she's actually comparing the metaphoric process of the lost wax casting to the release of rain onto her Ishta Devata, or Vishnu in this case. And you're seeing here also the microstructure of one of the bronzes, which in this case had a bit of the mold impregnated into the bronze. So now when I was talking about the Chola bronzes, this is one here which I had analyzed by atomic absorption spectroscopy and ICP-MS and so on, spectrochemical analysis by undertaking a micro drilling and then making the micro drillings go into solution and then undertaking inductively coupled plasma atomic emission spectroscopy. And one of the findings of the bronzes that I analyzed was that the tin content was less than about 15%. These are typically low tin bronzes, and the lead is added to make the bronze more castable. Because of course, copper is not very hard, it's a soft metal, and then tin is added to make bronze harder. And then lead is added to make the bronze more castable. But what happens when we keep adding tin to bronze? As you can see, this is a phase diagram of the copper versus tin system to see what happens at different temperatures and different compositions of tin. If we keep adding more tin to bronze, it actually becomes very brittle in the as-cast condition. And typically, this is a bronze from Thailand, which is actually of 22% tin, but you can see that the hand is broken off. And this is because as-cast bronze at 22% tin is actually very breakable, and as you keep adding more and more tin. But it's very interesting that already in South Indian antiquity, in the Iron Age, and this is a bronze from Iron Age Adichanallur, and I'll come back in a bit more to the dating of those. Already in the Iron Age, they had isolated a particular alloy of bronze. This is beta bronze, as we call it, which has about 23% tin. And at this composition of bronze of 23% tin, at a higher temperature range of about 600 to 700 degrees centigrade, the bronze becomes very plastic, so it can be hot forged very considerably at this high temperature range. And also, the brittleness can be reduced by heating this bronze to a high temperature, annealing it, and then quenching it, so that the rapid quenching leads to the retention of this plastic beta phase. And that actually prevents the bronze from becoming too brittle. So this is how this very early bronze vessel from Adichanallur has been made, where you can see what the microstructure is telling you. This here is the microstructure of a Chola bronze, which is a leaded bronze. You see the dendritic as-cast structure and this coppery color telling you that there's not too much tin in it. And the lead has segregated into the intergranular spaces because lead is immiscible in copper. But this is what the beta bronze looks like. It has no lead in it, but the quenching results in the retention of this needle-like beta phase, which you wouldn't see otherwise. So this is what happens if you don't quench a bronze of about 22 or 23% tin. You find the formation of this intergranular alpha plus delta eutectoid, which is very embrittling. But if you quench it at a high temperature where this plastic beta phase forms, you get the retention of this beta phase. the needle-like martensite. And that's what gives unique properties to this bronze, where they were able to forge it to such a high extent. And also then the brittleness is prevented. And although there were some doubts that such a technique was actually being used in India earlier, I was also able to find an ethnographic parallel to that bronze working tradition in Kerala. And you can see this was in the early 90s, and I'd visited with my husband Digvijay, and we were able to identify this workshop. So you see here that this is a blank which was hot forged in the plastic beta temperature range, and there are these repeated cycles of annealing and hot working and then quenching. And even the modern vessel, if you see, has this typical needle-like martensite being retained. And when the bowl is polished inside, you can see how golden it is, which is why it was sought after. And this is what the outer unquenched layer looks like. So this is how ethnoarchaeology could actually prove that such a tradition survived in Indian antiquity. And what was also interesting is that you also see such vessels being found in the remote Nilgiris. And this is again a region to which I have a lot of family connections. My husband is also from the Nilgiris, Digvijay, and we're here at one of the Toda Mans. And there are these grave goods there of very high sophistication, such as these ear ornaments, which are now in the which were from the Breeks collection, and they're now in the British Museum. And we were also able to identify old gold workings in the Nilgiri region. And this is another vessel of such a high tin composition. And you can see here that it has a beautiful floral motif. And I'm tempted to think that this is actually the depiction of the Nila Kurunji, which is one of the very beautiful flowers which simply covers the entire Nilgiri landscape, and it blossoms only once in 12 years. And you also find it referred to in the Tamil Sangam poetry and the love poetry and so on. So the fact is that from these analysis and ethnographic studies, we can also trace back some of these old legacies. And what was also interesting was that I have then recently been involved with the DST Shri project to do some analysis of artifacts uncovered from the Iron Age excavations of Adichanallur and also Shivagalai. And these, of course, have been also in the news, and I'll come back to that later about these very early dates for the Iron Age. But what was also interesting is that we looked at some of the vessels from and some of the artifacts from Adichanallur and Shivagalai, and lo and behold, we're getting very early finds of beta bronze of about 22% tin composition. And in fact, this sample from the ASI Adichanallur excavation has been dated to about 1200 BC. So we can say now that it is probably a tradition which is already long prevalent in South India. So we don't necessarily have to see these very sophisticated artifacts as imports from somewhere else, because that was what had been done earlier, because it was thought that perhaps these Iron Age cultures don't have that kind of sophistication, so these grave goods must have been coming from somewhere else. But this is how archaeology helps us to understand and contextualize some of these findings better. And since I'm here at PRL, I also wanted to mention some of the work on the compositional analysis of the South Indian bronzes using the techniques like the inductively coupled plasma optical emission spectroscopy. And we had analyzed for 18 elements, including the major, minor, and trace elements. And as you know, the major elements, which are alloyed to copper, like tin, lead, or zinc, can vary randomly. But what is useful with the analysis of the trace elements is that sometimes they can give clusters, which help us to identify the sources from which particular bronzes were made, or if they're clustering together, then we can see some patterns. And what I was able to see was that for certain stylistic groups, there is a meaningful clustering of the trace elements, especially when taken together with another analysis technique, which is known as lead isotope ratio analysis. So for about 60 artifacts, which were in the Victoria Albert Museum and also in the Government Museum, Chennai, we managed to do the lead isotope ratio analysis. And for another 150, I had done the compositional analysis. So putting together the trace elements and the lead isotope ratio analysis, one was able to get a certain clustering, especially for the chalcophilic elements like cobalt, nickel, antimony, and bismuth. And so these were clustering together in meaningful ways. Now, one of the reasons why we had to look at compositional analysis to do this kind of characterization of the bronzes basis on styles was because the South Indian bronzes are mainly solid cast, which means that they were all made by first shaping a wax model, a solid wax model, and then covering that with numerous layers of clay and then getting the mold, so that when the metal was poured in, you're getting a solid piece of metal, as you see here from this radiograph. So there is no absolute method of dating metal in that way. Whereas with, if you had, for instance, some charcoal, then you could use carbon dating. And in fact, you have another technique of casting bronzes, which is known as a hollow casting, which I'll come to in a minute, where you could have found some traces of, materials for carbon dating, which, as I said, we couldn't do for the solid cast images. Now, I was talking about the lead isotope ratio analysis, which some of you may be familiar with, but basically the reason why we can use it for archaeological provenancing or characterization is that the lead isotope ratios of different ore deposits across the world can vary in a measurable way because of the different histories of formation of the uranium thorium cycles and so on, out of which the lead isotope ratios, out of which lead is also formed. And so this is why we get different lead isotope ratios, which are characteristic of ore deposits of different parts of the world. And just to show you this plot, since we are here in the Western Indian region, we see here that the Zawar ores are all clustering up there. And as you know, Zawar in the Aravallis was also, I don't know if many of you are familiar, but it is also linked to the early smelting of metallic zinc, which I'll come to in a minute. So these are polymetallic ore deposits of lead, zinc, and so on. And so this had been undertaken for the analyzed South Indian bronzes. And of course, most of them tend to cluster over here, and we haven't actually identified the ore sources for all of them, because sometimes the ore deposits may be worked out and we don't have the lead isotope ratios for all the ore deposits. But for some of them, we did find some meaningful correlations. For example, since we're here in Western India, this is a beautiful Jain image of Santinatha, one of the Tirthankaras, which is in the Victoria and Albert Museum, and a very large image, actually, about a 1 meter or so. And this image very clearly had lead isotope ratios which fitted the Ambaji mine, which is again a Western Indian mine here. So the fact that it matched very clearly this source in Ambaji means that the lead was coming from this deposit. And what is also interesting was that this image was found to have about 21% zinc or so. And it's quite interesting because it's possible that such a large image with so much of zinc in it, I'll come to that in a minute, was it made of metallic zinc or of cementation brass? So these are the kinds of questions before us. And what was also interesting is that a South Indian image, one South Indian image from Kanchipuram, which is this Buddha figurine. So this clearly also had lead isotope ratios which matched Ambaji. So, and this is a 13th century image, about the same date as the Santinatha, which is inscribed to about 12th century or so. So we do know that metal was moving back and forth from North India to the south and so on, at least by this time. And just to also point out another example of how, even if you're not able to clearly identify ore sources, these kind of provenancing techniques can help us to tell apart the styles to some extent. This was a beautiful image of a Yakshi, which is in the Victoria and Albert Museum, a very tiny image, which is about the 1st century or so, which the museum couldn't decide whether it was Kushan or whether it was South Indian. Because the style is a bit similar, of course, to some other Shatavahana images of about the 2nd century. But I did find that the lead isotope ratios did not match any of the North Indian and Kushan and Mauryan coins and so on, whereas it did fit some of the South Indian material I was looking at. So it's quite likely that this was actually, did have a South Indian provenance also from the ore sources and so on. So, of course, since I mentioned the zinc smelting, we do know of 2 very remarkable stories of technology transfer from the east to west, from India to Europe, where there was semi-industrial scale of production of metallic zinc. And it's also likely that William Champion, who's credited with the zinc production in Bristol in 1736, was also inspired by the Zawar process of zinc smelting. And I'll come to that in a minute. And this was also designated as an ASM landmark. And this was awarded in 1988 for the Zawar mines, which is in the Aravalli region. And the other artifact which has been accorded the ASM landmark in India is the Delhi Iron Pillar, which was awarded actually in 2015 due to efforts of various scientists, including ourselves at NIAS. We were also involved in providing the dossier for the award of the ASM landmark to the Delhi Iron Pillar. And talking about the Zawar process, so what was distinct about the Zawar process is the following. Because zinc is one of those metals which cannot be smelted very easily, because the minute you heat it to a high temperatures, to the temperatures where it becomes molten, the zinc core, when you heat it to a high temperature, the zinc core actually, it doesn't, it's not easy to smelt because the zinc sublimates immediately as it is, once it is reduced, the zinc just vaporizes and sublimates. So that's why what is innovative about the Zawar process is that they had designed a very special process of distillation, whereby they packed the zinc ore inside these retorts. And this is a downward distillation process where the ore was packed in these retorts up here, and these stems reach down. So this is the condenser portion. And the furnace was heated from the top, so that what happened was that the ore, once it got reduced, it goes through a drastic cooling process. So it's a condensation process, and then the zinc vapor cools and collects here as ingots. So this downward distillation was a very specialized process which seems to have been developed earliest in Zawar, and we have evidence from the retorts which have been studied by people like Paul Craddock and so on, going back to about the 11th, 12th century. And we also have at that time records such as the text by the King Somadeva of the 12th century period, the Rasendra Chudamani, where he mentions the Musa, which was shaped like a brinjal. And you can see here how it matches well to this crucible of clay, and resulting in the distillation of zinc ore. And here you can see some of the retorts which were also found in Zawar. And I was also struck, I happened to put in some of these dance photos also, thanks to Subhabati's interest in dance and so on. And, you know, in Bharatanatyam, you keep using the term rasa, which is conveyed as a distilled aesthetic essence. And you see that the same term is also used in alchemical texts. Perhaps it referred to mercury, which is also obtained by downward distillation, but it also refers to zinc in many places. So this idea of the metaphor, again, between the metallurgical process and something which is also a more of an aesthetic and more of an abstract idea, these kinds of parallels is again very interesting to me. And here we've seen looking at the zinc retorts using XRF analysis, and this helps us to analyze the zinc-rich minerals and the iron-rich minerals and so on. And of course, then metallic zinc is also used quite extensively from about the 14th century under the Bahmani sultans in the Bidar region of North Karnataka to make this very beautiful alloy of the Bidri ware, which is a high zinc alloy, and you have this blackened features which come from the etching of the zinc alloy that you see here. And it also has a little bit of copper added, which from XRF we analyzed it was about a 6% copper. And then it is etched and inlaid with silver. And then the etching is what gives the blackening effect and so on. And I also put this because we talked about the excavation technique, and I'm grateful for this photograph to Pranav Patel, who's here. This is the Rani Ki Vav, which is a World Heritage Site of the Solanki period in Gujarat. And you can see, of course, the expertise in deep excavations, which also found in our step wells and so on. And I was also involved in a digital heritage project along with other institutions like IIT Delhi and so on, which was showcased at the National Museum in Delhi, where there was also a laser printed model of the Rani Ki Vav, along with other virtual reality displays and so on. And this is, of course, to also show the connections, the Solankis, because the queen Udaymati was married to the Chalukyan king Bhima. And you see the influence of the Western Chalukyan iconographic styles also. This is a Badami Chalukyan image of Vishnu from, which is now in the Bombay Museum. And you see the similar depictions here in this step well. So coming back to the lead isotope analysis, so there was a cluster there that I pointed out to you, which a lot of the South Indian images were clustering into. And so when one exploded that, it was also interesting where one could find that some of these clusters were correlating to particular dates of stylistic dynasties and so on. For instance, the Chola bronzes were clustering in this cluster one around here, and the later Vijayanagara bronzes were clustering up here in this ellipse. Of course, the Cholas ruled from about the late 9th century to the mid 12th century. And then you have the what is often called the post-Chola period, but I also call it the Chalukya Chola period because that is when a prince of the Eastern Chalukyan dynasty had also come into the Chola throne. And then the Vijayanagara period from about the 1336 to 1565 or so has a distinct style of its own. And what was interesting was that the pieces that we attribute to the High Chola period did have lead isotope ratios and trace elements and so on, which very neatly fitted this ellipse. And here is one of the inscribed Kali images with an inscription of about the 10th century, and another beautiful image of Parvati in the Government Museum, Chennai. And this is another Nataraja image from Velankani, which has also been attributed to the Rajaraja period with about 5% lead and 4% tin. So these all fitted the High Chola period. And then we had some of these images which were attributable to the Vijayanagara period, which fall into that ellipse up there. This is one of Varaha, Vishnu, and Bhudevi, and another Kaliya Krishna, which all have some very typical Vijayanagara characteristics. The ornamentation and so on is of a different style from the Chola period. And as I said, the Chola bronzes very sensibly had less than about 15% tin, though there were some exceptions. Some were brasses as well. And since we talked about the use of zinc, it's interesting that it's not as if the use of zinc and brass was unknown in southern India. You do have some very early examples here. And this is a very beautiful votive octagonal votive vessel, which was in the Victoria and Albert Museum collection, which I had analyzed. And this had 17% zinc and 8% lead and 10% of tin. And you can see here at the bottom, it has these elephants and so on. And this image, interestingly, had lead isotope ratios, which very closely matched this set of coin ingots, zinc coin ingots, metallic zinc coin ingots, which had a Brahmi inscription, which is attributed to the southern dynasties, early Andhra dynasties, perhaps the Vishnu Kundin dynasty. And so this was also found in the Krishna Delta. So these seem to be early examples from the Andhra region, early historic, about 4th century or so. And it's interesting that one of the well-known scientists associated, or alchemists, Nagarjuna, is also said to have come from that region, so I don't know. But what is also interesting is that these lead isotope ratios of this deposit did not match ours. So there may well have been another source of South Indian zinc. So these are things to be looked into a bit more. And this is also one of the mines in the Agni Gundala region in Andhra Pradesh. And in fact, one of the Iron Age artifacts, which has been clearly dated to the 5th century BC, which I don't have an example of it here, but the photograph here, but a copper vessel from Koduvanal, that clearly fitted the lead isotope ratios of this mine, Agni Gundala. So clearly early mining was going on in some of these South Indian mines from about the, at least the mid 1st millennium BC as well. So it's not as though they would have been dependent for all their metal only on northern India. And that's also interesting and important to point out because some art historians like Vidya Deheja have suggested that there really wasn't any copper in South India. And so it would have had to come from Sri Lanka and so on. But when we look at it in a more nuanced way, there were several maybe not so prominent ore deposits in South India as well, but they were certainly there. And so we can't just rule out without further investigations. And I was talking about the hollow casting technique. And you can see here, this is an early Avalokiteshwara image from the Krishna Delta of the Andhra Pallava period, which was also fingerprinted to the early historic period. And you can see here that it is, why it is described as hollow casting is because there's another way of making these castings, which is that you can make a clay core and then put a thin layer of wax and then invested it with numerous layers of clay, so that when you pour the final metal in, you just get a very thin layer. So that also ends up saving on the metal. And in fact, a lot of North Indian images are actually made by the hollow casting process. And we can also see that that is a technique that seems to have come in from the Hellenistic influence through the Northwest. Some of the Gandharan images and so on also follow this technique of the hollow casting, which was very widely used in the Grecian and the Greco-Bactrian world and so on. And yes, and a very fine example, actually, this is probably the largest bronze casting from the Indian subcontinent, the Sultanganj Buddha from Eastern India, which is now in the Birmingham Museum. And I just put this figure with myself next to it just for the scale. It is really a monumental image. And this is made by it's a post-Gupta image of about the 6th or 7th century, and it is made by this hollow casting method that I mentioned, where it has a clay core and then a thinner layer, which follows the Hellenistic traditions. And just to show you that I also analyzed some Buddhist images from the Chola period. This was fingerprinted to the Chola period, the seated Buddha. And this is an inscribed Lokeshwara, which is also gilded, which is in the Kadri temple in Karnataka, and the gilding is actually done by a process called the mercury fire gilding. And this is another very beautiful gilded image from Nagapattinam, which was in the Victoria and Albert Museum collection. And now we also know that, of course, although the Cholas were very prominent Shaiva rulers, they also patronized the setting up of a Buddhist vihara in Nagapattinam, and where the Srivijayan kings also were paying tribute. And as I said, this image had only about 1% copper. And that's also because for a fire gilded image, you need to have less of metals which can ooze out, like lead and so on should be less. So sorry, not 1% copper, it had 1% lead. So very low amount of lead so that the fire gilding could be done properly, where basically an amalgam of mercury and gold was applied, and then it is burnished so that the mercury gets burnt out and you get this gilded layer left onto it. And why I also put this slide in is to show that I had done the analysis on this spectacular Tara image in the British Museum. If you all have visited the British Museum, this is one of the most spectacular images there. And this is also gilded. And interestingly, I found that the lead isotope ratios of this very closely matched this image from Nagapattinam. And I think it's likely that there is a Tamil connection to this bronze because it was actually found in the northeast part of Sri Lanka. And it is a bit different also from other Sri Lankan images. This is a seated silver Tara image from Sri Lanka, whereas this image has a typical leg flexion, which you see very much in the Tamil bronzes. So it's possible that there were some connections here, which sometimes the analysis helps to pick up. And I should also say that the analysis of the South Indian bronzes were different from some of the Sri Lankan images that I looked at in terms of the iron content, because the Sri Lankan images had significant traces of iron. And that might not be surprising because there is one very iron-rich deposit in Seruvilla in Sri Lanka. So we're not seeing that much of iron in the South Indian images, maybe because the copper sources were different. And in this sense, I think I differ also from some recent findings that Dr. Vidya Deheja has made on the basis of the analysis of only 3 bronzes, where she suggests that it could have been a Sri Lankan copper source for the South Indian bronzes. But I think that the South Indian images, one can't jump to those conclusions, and that they don't seem that similar to at least the copper source in Seruvilla. One other very important finding, which I talked about in the morning from my studies, was that although we associate the emergence of the Chola bronze typically to, the emergence of the Nataraja bronze typically to the Chola period, I did find that the lead isotope ratios for the Pallava bronzes was different from the Chola and the trace element ratios. And one very important finding in that was the Nataraja bronze already seems to have been formulated by the Pallava period. This bronze in the British Museum was thought to be a Chola piece, whereas it fitted the lead isotope ratios better for Pallava bronzes, like this Kuram Nataraja. And this image is also dated by art historians to the Pallava period, because there is also the finding of a Pallava copper plate inscription along with the Kuram Nataraja and so on. And you can also see that actually there is a 7th century frieze in Siyamangalam, which has a leg extended in this typical posture known as Bhujangatrasita Karana, which matches this Pallava attribution for the Nataraja bronze. And one other very interesting study that I'd done, since we're talking about women scientists and astrophysics and so on here, with the late astrophysicist Dr. Nirupama Raghavan, was that there is this tradition in the temple of Chidambaram where you see this very interesting worship of Shiva both in the aniconic form and the anthropomorphic form. The anthropomorphic form is a dancing Shiva Nataraja, but the Shiva Nataraja is also evoked as Akasha or ether in this particular temple, in this aniconic form. And at this temple, there is also this tradition that in the month of Margari in December, when the Orion constellation appears right up in the horizon, and you can very clearly see, especially the star Betelgeuse, which is described as Arudra in the text. So there is this tradition of the Arudra Darshanam and Arudra Tandava Darshanam, where the dance of Shiva, the destructive dance, the Tandava, which is also in a way, the Ananda Tandava is a blending of destruction and creation, because Ananda, of course, is bliss and Tandava is destruction. So the coming together, as I was explaining, the morning of creation and destruction and so on. So, but the Arudra Tandava Darshanam is related to the observation of the Orion constellation up in the zenith. So we were wondering whether the iconographic position of the Shiva Nataraja might be influenced by this observation of the Orion constellation, because it's a very particular kind of depiction that you only find in Tamil Nadu. You don't find this version of the dancing Shiva anywhere else. For instance, in Badami and Karnataka, it is a different image of Shiva Nataraja with the Chatura Tandava. And it's possible that when you align the star positions of Orion, you know, the belt of Orion aligning along the waist of Shiva Nataraja, and the leg seems to point up to Sirius here. And there is also a leaflet from a book from Chidambaram, which one of the Dikshitas, Raja Dikshitas, shared with me, where this Arudra Tandava Darshanam has this drawing of the stars around the Orion constellation. So it's possible that this might have had an inspiring role. And you also get a lot of the verses like Manika Vachikar, which sings of Shiva Nataraja creating, destroying this earth, heaven, and all else. Adiyam Antamam Illadavar, the one who is without beginning and end. So there may have been this sense of observing the cosmos, which also influenced, you know, the making of the bronzes. And of course, they had plenty of time in antiquity to do all of that. I think I just have another 5 minutes, but I'll try to quickly wrap up some other findings. And I had talked about the beta bronze, but there is also another very interesting craft where the use of bronze of an even higher composition of tin is made with about 32 to 33% tin. And as I said, yes, this alloy does get very brittle, but there's a reason for seeking out this alloy of a composition of about 32 to 33% tin, because you can get a very good mirror polish with that alloy. It's very silvery and it's very hard with a very good reflectance. And this is the Aranmula metal mirror, which is made of this kind of composition of bronze of about 32 to 33% tin. So the technical challenge there would have been to how to reduce the brittleness while optimizing the specular reflectance of this alloy. And so it was very cleverly cast in a closed crucible cum mold process, where in this very thin blank, the metal would have been cast. And it's a closed crucible cum mold process because the metal to be alloyed would have been put here and the whole thing sealed. So that what you saw earlier in the Swami Malai process was an open casting, but this is a closed casting. So what that does, it reduces the oxidation losses and so on, and provides a more reducing environment. So, and we also use the thermal camera to try and understand the temperature differences. So this, you can see the closed crucible cum mold with the alloy, which has been placed here. And then it is heated face down on the hearth and tipped over. So you can see there's a considerable difference in the temperature between the part where the crucible cup is heated and the bottom. And this temperature differential is also very important because it leads to something which is closer to a more homogenizing chill casting kind of effect. And that's the blank which is then got. And then the blank has to be polished over several days. And here too, they use some very interesting aspects where they used powdered mirror blank itself, because it's a very hard and brittle alloy. So there is a certain amount of self-polishing so that all the defects get filled in. And this was actually the largest Aranmula metal mirror, which was made by the late Janardhan Achari, and this is all his family and daughter and so on. And this is all of us Digvijay and my daughter. This was in 2014. And another interesting dimension is that it does relate to some of these depictions you see. This is a very beautiful Hoysala image from Belur of the 13th century, where you see, this is of course in Karnataka, and you see that she's gazing at a mirror. And this mirror actually looks a lot like this wooden handle with the mirror mounted on it in resin. So this itself could have been used as a mirror. So it's a way of speculating, back on these processes. And as I mentioned in other talks, there are some examples of that kind of mirror from the Breeks collection from the Nilgiris cairns with about 30% tin and so on. And of course, coming to the topic of ferrous metallurgy, it's too vast. But anyway, I just wanted to make a mention of the celebrated iron pillar, which the late Dr. Balasubramaniam also studied. And this has a beautiful Gupta Brahmi inscription, which attributes it to the period of Vikramaditya II. And it has been proposed by Balasubramaniam that the inscription which refers to Vishnu Padagiri may be referring to the Udayagiri mountain, which may have been the original location. And we were able to also have a publication with him with the analysis showing this, the structure, wrought iron. Now, of course, I wanted to say that when we talk about wrought iron, which is what the Delhi iron pillar is, it's a massive wrought iron forging. Wrought iron basically contains very little carbon, less than about 0.04% carbon. And that's why it can be forged to a large extent. And so that the Delhi iron pillar would have been made by packing all these cakes of wrought iron. But what is very interesting is that there is also a long tradition of using higher carbon alloys, especially in the case of southern India and the wood steel, where this is a steel which has a composition of about 1.5 to 2% carbon in it. So what happens when you keep adding carbon to wrought iron is that, of course, with steel, it gets harder and harder. But at this particular composition of about 1.5% carbon, the steel had very special properties, which I'll very briefly touch upon here. So in the 19th century and 18th century, you had a lot of travelers who were visiting the south of India, and they mentioned the making of these steel by crucible processes. And what was basically happening was that the wrought iron was being packed inside these crucibles and then heated to very high temperatures under very highly reducing conditions, so that the iron got into the wrought iron to get this higher carbon composition. And this is a microstructural analysis of one of the crucibles that I found in Melsiruvalur in Tamil Nadu. And what is interesting is that this is the metallic structure, which is, you can see here from the globule here, that it is almost a liquid. Is the temperatures that were reached were very high. And also the prior austenite structure indicates that very high temperatures had been reached. So it had been carburized almost in the molten state at very high temperatures. And you get this pattern with perlite inside these, these hexagonal grains, and the cementite along the whitish cementite along the grain boundaries. And what is interesting is that these ingots, which were made of the steel, were then traded very extensively to West Asia and the Arab and Persian countries. And they were used to forge these blades, which were known as the Damascus blades, which have these alternating patterns of perlite and cementite. And they were much sought after for this pattern. And also because this steel at these high temperatures actually becomes very superplastic, which means that it can be extensively forged at high temperatures, which is why these ingots were very sought after. And of course, that term woods is also a corruption of the term ukku, which refers to the process of making molten in Tamil. And you also see in Tamil Sangam literature the term yegu, which comes up, which describes the processes used to make the spears, which you find described by the bards like Avayar and so on. And Zosimus, one of the Greek alchemists, also describes the process of spears and swords being made in the Indian subcontinent by he calls fusing molten iron in crucibles, which seems to refer to the crucible steel process. And why I put this in fact, PRL also has a role in this. Recently, there were these amazing finds which have been reported from Tamil Nadu, pushing back the dates of the Iron Age. And there were 4 dates from Shivagalai, the urn burials of Shivagalai, which go back to nearly 3000 BC, one from Adichanallur and one from Shivagalai, which were actually given to the top lab in for analysis by accelerator mass spectroscopy in Florida, Beta Analytics, and they came out with these dates, which I would say are around 3000 BC or so. And PRL also did some OSL datings, and they also got corroboratory very early dates. And this is quite astonishing if it pulls back the date of the Iron Age so early. And my take on this could be that because Tamil Nadu didn't really have a copper age in the same way as we see with the Indus Valley and also the Chalcolithic finds that you see in many parts of northern India and maybe Sanauli and so on. So then what was going on? You can't just leap from the Neolithic into the Chalcolithic. So what I've proposed in my article in Frontline, which I guess is also quite a bold take on it, but it's possible. So I've suggested that perhaps the Harappans, some copper smelters from the Harappan region had migrated via the sea route into Tamil Nadu because these sites, the Porunai sites, are very close to the coast, the far south, Adishnur and Shivagalai and the Tamraparni River, which is, the far south, the coast of it. And perhaps they didn't find the copper ores, and then they attempted doing smelting with iron ores and then accidentally invented iron smelting in that region. Because the dates, if we take the fact that they are from the top lab, if they are reliable, then we have to try and understand how this early iron might have been occurring there. And one very interesting aspect, of course, is that already in Alexander Rear's excavations of about 1900, there are certain bronze figurines and so on, which he had reported. I don't have time to go into that too much, which are in the Chennai Museum. And one very significant amongst them was this metal figurine, which has been described loosely as a mother goddess figurine. And what is very interesting, which was noticed already by some of us even earlier, was that it's very similar to the repertoire of the Harappan terracotta so-called mother goddess figurines, such as these, which you see in Harappa. And, this very similar way of treating these stringy things near the ear and this belt just below the waist and the feet and so on. So that's why I've tried to theorize that perhaps there was already some Harappan presence, which could have led to some innovations and leaping into more advanced metallurgy and so on. Anyway, these are aspects that we are working on still, and that's a whole topic, so I don't think I have time now to cover it. But I just wanted to here mention what we also do at NIAS is we try and do experimental iron smelting, and also because iron smelting is not as easy as you make it out to be, because, iron does not become molten until it reaches very high temperatures of about 1500 degrees or so. So you need to have a very reducing environment and strong draft and, sufficient charcoal and so on. And that's why I say that there would have had to have been some prior knowledge of pyrotechnology and copper smelting or something to come to the level of iron smelting. It's not such a trivial aspect. And of course, for now, very firm dates for iron smelting do come from Turkey and Kaman Kale Hoyuk, which is an early Bronze Age site, where you do see, of course, the movement from the copper bronze repertoire into iron smelting much more readily. So that is where you still have some very early dates of about 2000 BC. So our dates here from Tamil Nadu go back even earlier. So it is very interesting. But we do know that there is a long tradition of very skilled use of ferrous metallurgy here too, as we've talked about the wood steel, and dates for the wood steel finds of high carbon steels in South India also getting pushed back earlier. This is a site from Kodumanal, which the earlier dates had only been stratigraphic to about 3rd century BC. But again, AMS dating from Beta, Florida has pushed the dates back to 5th century BC. And these are again some crucibles which were used for carburizing the wrought iron. And you can also see here that there's evidence for diamond drilling and so on here with these quartz beads at Kodumanal. Again, diamond drilling is something you associate more with the Kambat and the Indus tradition here in this part of the world, Gujarat and so on. So whether, as I said, there was already this maritime connection which was contributing to the spurt in metallurgy. And here you see, this is another iron nail fragment of this ultra high carbon steel with the pearlite and the cementite network from Pattinam, which is a site associated with Musiris, which was an Indo-Roman trading port. And of course, we also know that by the early Christian era, there was extensive trading also with the Roman world. And this is a signet ring, which has a combination of Indian and Roman motifs. And there is also a tradition in, for instance, in in some of the Roman accounts, which refer to this iron from the Ceres. And the Ceres has been thought to refer to the Chera kingdom of this part of southern India. So it's possible that iron was being traded out here to the Roman world. And we also know that these sites, Adichinallur and Shivagalai, are on the Tamraparni River. And interestingly, the Roman accounts also talk about Tabropane, which is one of the places which, they had noted and so on. And Tabropane has often been associated with Sri Lanka. But I actually think that this Tabropane may be referring to Tamraparni, this region of the southern tip of Tamil Nadu, which may have already been, and it seems was already known to Greek sources. And so, it's a region of considerable antiquity. So this adds to this idea that where some of these technology transmissions and so on could have been happening, leading to these early innovations in technology and tradition. So thank you very much for your kind attention.
Thank you, ma'am, for a fascinating journey to the archaeometallurgy. And now floor is open for the questions. And I hope we have some time for questions.
Yes, sure. I have a flight to catch, but definitely.
So maybe we'll quick questions.
Hello, Professor Sharda. It's good to see you. It's like you have given a good insight about the Indian metallurgy. My question is related to the Zawar. Recently, I had a chance to visit Zawar GSI site and see those retort hilltops, hillocks, and the walls you have shown. They have mentioned that the ages of those walls and the retorts, they are saying it's more than 2000 years. But you have shown in one of the your article that it's around 1700 century they are mentioned. So what's the story? Means is it finished or it's already dated?
Yeah,
What is
thank
it?
you. Of course, my area of expertise has been mainly southern India. So, but Zawar, the initial work had been done, of course, by Dr. Hegde and then the team of Paul Craddock from the British Museum. So what has what I was talking about, the retorts, the actual retorts for zinc smelting, which they had dated by carbon dating, the retorts had been dated to about 11th, 12th century. Some of the walls and retorts that you saw. But I think there is evidence that the mining there was going on much earlier, going back, as you said, to about 2000 years, because I think some of the mine shafts themselves have been dated from the carbon, the timber found in the mine shafts to about the late first millennium BC or so. So clearly the mining was going on there earlier, but the clear evidence for the retorts is a bit later. Of course, that zinc ingot, which did not match the Zawar mine, that actually had a Brahmi inscription of 4th century AD. So where that was coming from, I don't know, but that is one of the earliest examples of metallic zinc. But the other aspect is that I also found that there was lead isotope ratios on some Hellenistic artifacts, Hellenistic brass, which Dr. Sophie Stoss-Gale from Oxford Research Laboratory had analyzed. And those were dated to about 4th century BC or so. And those were Greek or Hellenistic or 3rd century BC or so. And those actually match Zawar. I don't know what those artifacts were. It didn't match anything in the European world. So I think if we look at some of the analysis on objects, elsewhere, we might get more insights into all this. But I think at the moment, the retorts have been dated to about 11th, 12th century. So maybe further excavations, if they were to come out with more evidence, we could push those dates back as well.
Any further question? Professor Kumar.
We made the steel here, but the swords were made in Damascus. Why did we not make that swords here?
Yeah, hello, Dr. Kumar, but thank you. Well, definitely, I think the mastery of the sword making traditions that you see in the Ottoman world or in Persia and, the Arab world, and of course, Persia as well. You see some really, wonderful examples. I won't say that they weren't there in India. You do have a lot of very good examples in the Mughal and Rajput armories and various museum collections. Also, probably the Nizam's collection and likewise Mysore and so on. But one problem, of course, is that if you see what happened after the mutiny also, the British actually set about destroying a lot of the Damascus sword blades which were in India because they saw that as a threat. Of course, by that time, the warfare had already moved to gunpowder and so on. But there is the records, like Egerton of Tatton talks about a lot of the armories being destroyed. And in fact, they say that there was a special shearing machine as well for destroying the armories. So I guess a lot of it also got destroyed. So we really can't say. But I also found that some of the steel was also being used for everyday, use. It isn't always that they were necessarily being used to make the fancy swords because, even today you'll see in Telangana, many of the toddy tappers' knives are actually of wood, steel, and so on. So I think we haven't done enough of the analysis on the other kinds of artifacts to see. But I would say it's also true that somehow it was to that extent, those beautiful swords and that tradition that you see in, for instance, in the Ottoman tradition, I've seen fantastic things, even wood steel mirrors and things like that, really amazing things being made, scissors, and, that finesse of workmanship is something which one has to grant that it was also, part of the metalworking tradition in that part of the world, the Islamic world and so on, yeah.
The swords that I have heard about here in Rajasthan, the Shirohi is very famous for making swords. Is that still any connection with the steel that you are mentioning?
Well, yes, I think we need to do more of this kind of documentation because there are many of these, traditions which are still surviving. And in fact, in Rajasthan, you also have, here what I talked about is where the intrinsic ingot of woods itself has the high carbon, composition of 1.5% carbon steel. So it can be forged into this blade. But there's another way which was used to arrive at a combination of low and high carbon steel. And that was actually what we call the pattern, the pattern welding method, and that was also followed, I think, in Jodhpur and so on, some of the Sikligars, which were the traditional community of swordsmiths, where you would hammer the low carbon iron and then the high carbon iron, alternately and so on. So you get in a manual way that kind of layering. And that was also found, in fact, in the Japanese swords, the samurai swords, which take it to an even more extraordinary kind of level where the high carbon and low carbon steel was, they kept forging it till you get a man-made pattern, rather than the intrinsic pattern. So these are all the variations. So I think there were a lot of very skilled swordsmithy techniques, of course, which we probably have lost or have not been documented enough and so on. Yeah.
Professor Sanjeev has a question.
So thank you, Professor Sarda. It's again a very nice talk. I was wondering about the sampling of the precious statues, like from the ones there in British Museum. I mean, they call it British Museum, but there is hardly anything from Britain. It's all from Africa and India, basically. So how do they sample it? Like, because this geochemical analysis is basically destructive, right? Most of them. So which part of the statue they kind of a sample, and how do they commission it? Like, does the museum commission this kind of study, or how does it go about?
Yeah, well, this is always a problem for us as archaeometallurgists. Of course, I was doing my doctoral work there, so I was trained in the best practices. And I have to say, we had very generous curators at the Victoria and Albert Museum and the British Museum and the Government Museum, Chennai, from which I also took a lot of samples. So I basically used a small handheld drill with a tungsten carbide drill bit, because tungsten carbide is very hard and it can, drill through, but a very tiny drill bit of about 1 millimeter drill. And I mean, a 1 millimeter diameter. So you would, and I would have chosen some very discrete, I mean, frankly, even if you go now, many of the objects that I sampled are still in the Government Museum, Chennai, but you'll never find out where it's been sampled because it's in a discrete location, like the armpit or whatever. And you do have to get in about, say, 1 centimeter deep, so that you can take out at least about 50 to 100 milligrams of drillings, at least 50 milligrams, because, it depends on the particular analytical technique. Some analyses you need, they're very high precision. So even with 5 milligrams, you can, get the solution for the plasma spectroscopy or whatever. So of course, in those labs abroad, they did have those kinds of facilities. I did it at the Royal Holloway and Bedford College, which is in London. So So I went around personally taking all of these samples. And I have to say, of course, one thing is that the curators in Western museums do tend to be enlightened about the need for scientific research and so on. So it was a collaboration. And I think since then, I find it very much more difficult. Or at least I think that time in the 90s, early 90s, there was a lot of interest. Maybe now all over the world, they're getting more cautious and they probably won't allow it. And now, of course, a lot of times I find, especially in India, they say, oh, we'll just do XRF. Okay, we have our XRF machine as well, which is totally non-destructive, as you know. So you do get a compositional analysis with XRF. But the XRF, the problem is that it's a surface analysis technique. So you can't get past the corrosion and so on. So it's not really as sensitive as you need. So you really need to do this bulk analysis. But now we do have techniques maybe like the laser ablation where you need just a small solid sample, maybe the small drilling or whatever. So the techniques are getting more sophisticated. But yes, I mean, when you talk about the museums, I have to say one thing I'm grateful for is that at least they're preserved and they do allow research. In fact, I'm hoping to go and do some of the XRF work of the British Museum collection of the Nilgiri gold, the Briggs Museum and so on, Briggs collection, because gold is easy to analyze by XRF because it's not corroded. So yeah, I think we need to come to a stage where we preserve our artifacts and also allow research to really get a good idea of the history of science and technology, which we are doing, but even so, I think there's scope there for better, more improvement. Yeah.
Thank you. I have a question. I saw that people have started dating steel. Okay.
Yeah.
Now, is that the carbon which is there you are trying to date it? What is it that, how are you dating it by radiocarbon?
Yeah.
And that carbon would be, did they use wood to put the carbon into the steel, or what carbon was used in ancient times?
Yeah. So actually, this has been a recent technique trying to do direct AMS dating on the steel sample. So what he's talking about, of course, as I said, is that steel is an alloy of iron and carbon. So there's some amount of carbon. And especially for the high carbon steel, which has about 1 to 2% of carbon in it, it's easier using AMS because, there's enough of carbon in it. So actually, one of the sites that the Tamil Nadu report had commented on, a steel sword from Telanganur, which a Korean scientist had analyzed with Rajan, and that had been sent for beta to beta analytics for, it had been sent to Arizona for radiocarbon dating. So one of the problems that happened with that was that it was giving very widely different dates. It gave some date of about, say, 1300 BC and another which went to really much older, 2000 BC and on. So it turned out that actually it also depends on how you sample it. Like if you use a diamond blade to cut it, you could be mixing some carbon through that. Yeah.
My question is not that.
Yeah.
If coal is used,
yeah,
okay, they are dead carbon. They won't give you any age. So most likely they used some kind of wood.
Yes.
Right.
No, of course,
So,
this is the point that for the wood steel itself, I don't know if I made that clear, but the carburization of the wrought iron was done by adding carbonaceous material like leaves and wood specimens and so on, so that the
not
carbon would have...
inorganic carbon, not like limestone or
No,
things like that.
not diamond or something, but actually
Limestone.
yeah, not limestone either, but using organic sources of carbon like wood and leaves and so on. So that's the idea that might have been what has contributed. But you're right that actually AMS dating, direct dating of steel and all, it's still a little in the developmental stages. It's not as conclusive as,
No, if you have carbon, we will date it. That's not an issue.
Yeah.
But what carbon? Is
Yes.
it
No, in this case,
dead
if it is made by this crucible steel process, then it should be organic carbon. Yes. To answer your question.
Any further question? If not, let us thank the speaker once again. And it is time to felicitate our today's speaker, Professor Srinivasan. And to do the honors, I request our director, sir, and Professor Shubhabati to join. Now, I hand over to Dr. Pragya for concluding the event.
So as we come to the closing of this enlightening talk today, I extend a heartfelt vote of thanks on behalf of Bibha Chowdhury Memorial Committee from PRL and PRL Ka Amrit Vyakhyan as well. First and foremost, I extend our deepest gratitude to our esteemed speaker, Professor Sharda Srinivasan, for delivering an illuminating lecture on archaeometallurgy. Ma'am, your profound insights into the scientific and historical dimensions of metallurgical practices have significantly enriched our understanding of this interdisciplinary field. We truly appreciate your time and efforts that you dedicated for sharing your knowledge today. A special note of thanks to our director, Professor Anil Bharadwaj, for his continuous guidance, encouragement, and unwavering support in fostering a culture of scientific inquiry and intellectual engagement at PRL. I would also like to express our sincere appreciation to Professor D. Palamraju for his invaluable support in organizing this event and for his dedication to promoting academic excellence. Heartfelt thanks to the Bibha Chaudhary Memorial Lecture Committee for their meticulous planning and efforts in ensuring the smooth execution of this event. I particularly thank Professor R.D. Deshpande for his time today, Professor J.S. Ray, Professor Sanjeev Kumar, Dr. Sheetal Patel, Dr. Yogita Kadlak, Nandini ji, Shivangi, Falguni, and Sudhanshu for their valuable support. We also extended appreciation to CMG, CNIT, library, canteen, purchase, stores, administration accounts, and CISF for their cooperation. Last but not the least, I extend my gratitude to all the distinguished guests, faculty members, students, and attendees for being a part of this talk. Your presence here is highly appreciated. So as we conclude this 5th Bibha Chaudhary Memorial Lecture and 102nd PRL Ka Amrit Vyakhyan, I thank everybody and I request all of you to join for a cup of tea outside. Thank you.